All right, so everybody online can hear me? Just assume that's a yes.
Yes.
just assume that's a yes. All right, so let me switch over to for today, for last class you did flatten, for today you did merge, right? Okay, so let's look at merge. For next class, you'll do the sort side of merge. And but we're going to start talking about variable binding and scoping stuff today in preparation for our first interpreter. But let's go through our merge thing first. Brocker, did we figure out that Clancy is the one who made us do flatten in class and then I assigned it? Was that a thing? Yeah, I'm not a fan either. You're right. He like unmutes himself and decides there's just not a whole lot to say. what am I supposed to do with this? Yeah, see, it was just sitting here.
I don't remember us doing it.
I don't either. I think we did like a simplified version, but it would not have worked for it to like work.
So where did that come from? Because I don't recall writing it. It's been one of those weeks.
Was it Mr. Gonzalez?
Mr. Gonzalez doesn't have his code. He codes a lot, but none of it's accurate. He does a lot of keyboard banging and then spilling liquids on the keyboard on purpose. It's kind of a jerk, is what it comes down to. All right, so then let's look at merge here. So if you remember from like a merge sort, so merge sorts, they there's a divide and conquer type algorithm where it keeps dividing the list in half until you get two partially sorted lists. And what I mean by that is you look at this, hold on, am I sharing yet? I'm not sharing yet. Way to go there, Clancy, by the way. I don't know. It's hard to find good help, Brocker, is what I'm saying. So you see here you have two lists, the list 1.4 and the list 1.2.8. These lists in and of themselves are sorted lists, right? So what we're trying to do is we're trying to merge these lists together into a single list that is sorted. Okay, so is this really a 2-star? Huh, whatever. All right, so let's go write the merge here. I'm just gonna dump this. All right, so is that big enough? See that? So we'll define merge to be a lambda. And this guy is going to take in two parameters, right? Two lists of a list of numbers. They dictate, yeah, probably list of numbers. List of integers, fine. LOI1, LOI2. All right, now we're going to have a cond in here. So the one possibility is that both lists have stuff in them, right? So if both lists have stuff in them, then we need to compare the cars of those two lists. And the winner becomes the cons onto our running total, right? But if both lists are empty, then we are kind of at the end, right? We've placed everything. All right, so let's handle that part first. So we'll say, and null LOL, LOI1, LOL, null LOI2. If both of those things are true, and we need one more guy here, then we'll just boil down to the empty list, right? That's our end condition. We've placed everybody. We need to stop our cons, the same pattern we've done all along. All right. Now, if they're both not empty, that means at least one of them has stuff in it, right? But they might both have stuff in it. So if they both have stuff in it, then we need to compare the first elements. But at this point in time, I can't just assume they both have stuff in it. So what's the next question I can ask? How do I ask, do they both have something? So if they both are not null, then I want to, well, I can make this look scarier, right? I can then do an and, but let's keep it somewhat clean here. So if they're both not null, then I want to ask a question. I know I can get the car from each of them. Has the book introduced a let yet? Or you don't know what I'm talking about? Okay, so we'll assume no then for a moment, and I'll insert one here in a few minutes. I'll introduce a let. Like whether it introduced it yet or not, I don't know what you're talking about. All right, so if they both have cars, that's effectively what we're saying here, right? Then we'll ask the question, if the car of LOI1 is less than the car of LOI2. If that's a true statement, that means that we want to cons on the car of LOI1 onto calling merge again, right? So we'll cons car LOI1 onto merge, passing it coulter LOI1 and LOI2, the current LOI2. Otherwise, cons the car of LOI2 onto the merge of LOI1 and the coulter of LOI2. Yeah. So if both of them are not null, both have stuff. If the car of the first list is less than the car of the second list, then we'll cons the car of the first list onto whatever merge returns of the coulter of the first list and all of the second list. Otherwise, we'll cons the car of the second list onto whatever merge returns on the entire first list and the coulter of the second list. That make sense? All right. Next con is if we have a null LOI1, then we want to cons the car of LOI2 onto merge of LOI1 and the coulter of LOI2. Like that. Else, we must have a null LOI2. Cons the car of LOI1 onto whatever's returned for merge coulter LOI1 and all of LOI2. Like that. So that if we call merge on the list 1, 2, what was our example here? 1, 4, 1, 2, 8. get the 11248. Go ahead.
So in my code, at no point do I have it being empty list. Is that technically incorrect?
Um,
You always use it under the empty list or something?
well, yeah, I mean, you're using conses, right? Or are you using list? Okay. Yeah, I mean, cons needs to have a stop case. So if you're using cons, that at some point you have to say the second parameter of cons eventually has to be a list.
Right, but like one of the first things you ask is if it's null, then you return the empty list.
Oh, well, you could also just return, you know, LOI 1 or something. That's a variable that contains the empty list.
Right, right, okay.
Yeah, it's the same thing. Is that what you were doing? Okay, so questions about merge.
I have a question.
Sure.
On the bottom, when you check if the LOI1 is null, I mean, if that's null, why don't we just like print out LOI2? Because they have already started.
Right.
Like in
Yeah,
order.
you're right. You're right. We could. So he's asking, since we know that LOI 1 is completely done, why don't we just cons? Actually, we don't even need the cons. We can just say LOI 2 here, right?
Yeah, that's what I'm thinking.
Like that. Why process the rest of a list when we know it's always going to be the winner? Similarly here, we can just boil down to LOI 1. Like that. And it'll still give you the. So the idea here is if we've run out of things to check in LOI 1, why continue this charade? We can just bail now. Now, with that in mind, if we assume that one of them becomes empty, then this guy never will occur, right?
Yeah.
Which means that we'll always get our final list from one of those two, which means we can actually dump that and still have a working solution. Because that whole first con was based on making sure that I eventually have a list. And now I do. I'm guaranteed to have a list. All right, other questions about that? But if you liked the first version I had there, the first version probably is the one that follows our patterns the most closely. This is a more efficient version. This is better, this version here. But if we're operating off of, you know, plug and chug patterns, the first one is, you know, recursively define data, call merge, and even though I'm wasting my time, I'm just going to keep calling it till it's done. Okay, so with that in mind, for next class, you're going to do homework 6 here, which is both of 129 and 130. They're actually the same assignment. The second one just requires you to give it a predicate instead of a less than or greater than for sorting. But the first one is a merge sort that can work hand in hand with what we did here. So what does merge sort do? If we just think about how merge sort works. Merge sort ultimately produces something that looks like this. 2 partially sorted lists, right? And so merge sort ultimately does that for us. And then we can call the merge that we just wrote on that to get them actually sorted. So we've already written the sort step. We just needed to, well, we've written the merge step, which is the last part of the sort. So now what you're being asked to write here is the division over and over again until you are set up with 2 lists, usually 2 1 lists, right? That we say these are trivially sorted. and then you bounce back up, and now you have a, you know, 2-2 list or something like that. You call merge on them, you know, and then those are sorted and so on and so forth. So 1.29 should be done in terms of 1.28, the merge. Right, make sense to everybody? All right. And Clancy, you should do 1.29 twice. All right, so let's talk about variable binding. When I talk about the scope of a variable, what am I talking about? Go ahead. Okay, so where I have access to that variable had to be bound somewhere, right? So somewhere in my code, I created a binding for a variable. So somewhere, if we're thinking like Java, I might have said int a is equal to 6. This creates a binding of the value 6 to the variable a. That's a binding. Then the scope of that variable is wherever I happen to have access to a. And if I have a more local version of that a, that means I have a more local binding of that variable, okay? So do we understand based on this right here what this word binding means? We are binding a value to a variable name, okay? That's what variable binding is. Whereas scope is where we have access to a variable based on where it was bound. And then we'll throw out there, variables always resolve to their most, put that in caps, most local, historically I would have said most local definition, but we're going to say definition and then I'll throw binding in there. So really definition and binding are synonymous in this example. So when we define a variable, we are binding a variable and a value to each other. All right, so nothing new here. This is stuff we're already familiar with pick your favorite programming language. We define variables, we have access to those variables wherever we have access to them, and a variable always resolves to its most local definition. That's the purpose of what is coming up next here, which is a variable environment. All right, so we're going to be starting to think about variable environments. But now at the same time, we want to think about this, this idea, and I know I have this, this is pretty, I can't read that. You can read that. Can you read that now? Clancy, you got that?
Looks good.
That looks okay. All right, even I could have read that, so we're good. All right, so we're gonna go back, and this is nothing new. We've seen this, I just threw it up there. So this is one of our grammars that we're using, kind of our simplified lambda calculus expression. That's gonna get significantly less simple as we go through here. But we're really thinking about whether things occur free or occur bound. And this goes hand in hand with variable binding here. So let me ask you this, based on this grammar, remind me, what's each individual rule of a grammar called? So this whole thing is a grammar. This first line, the second line, the third line, each one of those is called a what? You got nothing? Shouldn't we be, I've said it a bunch of times. I think I said it today. I might have said it today. No. They're called productions. Productions of a grammar. The rules of a grammar, the productions of a grammar. Now, I'm never going to test you like over like stuff like that. I'm not a real big vocabulary person, but you should know what they mean. And more importantly, if I say it, you should know what I'm talking about, because I sometimes just randomly say things. And I don't know that I didn't explain it to you. Didn't we have that last year with recursion or something? Or was it 2 semesters ago? I assumed I taught some concept and then I tested you on it. I never. Yeah, Sarah was ticked. Her tires were slashed. I mean, it was there was stuff. I really thought that I'd covered that. See, I don't know what I'm doing. Somebody's going to keep me in line. Like I wasn't going to cancel class. But oh, by the way, my illness from Tuesday is not COVID related. It's my same stomach issue I've been having. But I wouldn't have canceled class, but my wife made me go to the emergency room. Why? So I sat there for like 7 hours for them to tell me we don't know what's wrong. And then the next day it was fine. They just gave me my same antibiotics again. I'll eventually get immune to them, and then they'll have to take it seriously. Okay, so in any case, we have these productions. Now, we're talking about variable binding here. Out of these productions we're looking at, where does variable binding occur? So we want to think about the meaning of these productions. All right, I think at one other time I kind of gave names to each of these, but maybe since we don't have it in front of us, we'll just assume we forgot. Is that a safe assumption, Brocker? Yeah, this in one ear, out the other one type thing. But you know, if we start looking at this lambda calculus expression as kind of our first baby language, that's really what it is. It's a representative of a very simple programming language that we can't do tons with, but it's still a programming language. And we have 3 rules here. And we look at that first rule, an identifier. So if I go over to like Java, and I just write something like, well here, we'll just put it on the next line here. If I just say S, this is an identifier. What is that guy? What am I expecting S to be in that context?
Hello.
Yeah, hello. It's a variable. It's a variable that we get resolved in, you know, the current scope, whatever the variable environment. That's where we're kind of heading towards here. We are going to be implementing the thing that happens between these 2 lines, right? We have a binding. We're not going to actually have this kind of binding for a little bit, but this is a binding, right? We're binding the value hello to the variable S. And then we have a situation where we have that variable being used in the wild. And when you see a variable name, what do we do to it? We resolve it. We got to go look it up somewhere. Somewhere we have this collection of name value pairs, and we have to look through that collection in the most local scope first to figure out what is the most recent value associated with S. Okay, so this would be a variable expression, probably. All right, so back in here, this guy right here, we might call that guy, that particular production of a lambda calculus expression that is just an identifier, we might call that a var expression. An expression that is a variable, and what do we do to those? We resolve the variable. All right, now, what's the second production? What does this guy look like to us? Well, what's a lambda? Remind me what the definition of a lambda is. Doesn't necessarily mean that's the definition of this one, but it is. Unnamed function, okay? So right here, we're probably looking at a function, okay? We are somewhat limited here, because usually if we're writing functions, we can have, you know, any number of parameters, right? But in our language right here, we're stuck with exactly 1 input, okay? So we might call this well, maybe we call it a lambda expression, but really it's like a procedure expression or a function expression. That's what this guy means, right? This is our somewhat hard-coded, you have to give me no more, no less than 1 parameter. That's what we're stuck with. All right, so this is the way we describe a procedure in our new simple language. Okay, what's the third one? We can look at it and say, oh, it's a list containing 2 lambda calculus expressions, 2 of these guys. But what does it really mean in terms of the grammar of our language? When we use that third production? If I'm writing code here, when would I use that third production? What am I trying to accomplish? What would the output of that be? I'll highlight there so you can see where the lambda ends. Actually, will this work? It's technically, I want to make sure it matches up to our So we're not giving this ability yet. We don't have the ability in our language to actually define variables, but assuming a variable was able to be defined one way or another, this would be a legal lambda calculus expression, right? Which production is that guy? Just an X is this dude right here. He's an identifier. And what do we do with identifiers? We resolve them to their value. All right. Is this guy one of our productions of a lambda calculus expression? Is it a lambda that takes exactly one parameter and then has a lambda calculus expression after it? I guess technically not by our current definition. So I would actually have to say something like that for it to really be legal in our current simplified language. I mean, this language really hamstrings us. We can't do very much with it. All right, so this is a lambda that takes one parameter and then whose body, the body of that function is another lambda calculus expression. And then the second element of this guy is also one of our lambda calculus expressions, which is just a lambda. Now, is this something, is that legal by our grammar? Is this guy a lambda calculus expression? Yep. Is this guy a lambda calculus expression? Is this a list of two lambda calculus expressions? Is that one of our productions in our grammar? It is. But if you looked at this, what would you expect the result to be here?
List 77.
Well, I'm not actually even using X right now. I'll even just take that out. So this version of the grammar says, typically we might call this an app expression. And you've seen this before. If I say lambda a, I'll just go back to what I had before to give us a less hamstrung example. And then I pass in a 7 there. I know I misspelled lambda. All right, so this is a list whose first element is a procedure and whose second element is the input for that procedure. So the 7, so that's why I would call the list containing two lambda calculus expressions, I would call that an app expression. That is an expression whose first element is probably a function and whose second element is the input to the function. So I'm passing a 7 in for A, which creates a binding for A. And then I'm boiling down to 7 times 2. So this will give me a 14, right? For the second one. But notice the output of the first one. The first element of my list is a unnamed function, right? That takes a single parameter in and boils down to whatever that parameter was. Go ahead. Are we recursively calling this?
Not here, but like if we were to take one of the classes that we've been doing.
Potentially. Yeah, well, I mean, our language doesn't support recursion yet, but if we go down that path, you could potentially have more local bindings. Every recursive call would have its own environment, which would potentially have its own version of the local variables. You know, if you think about like factorial of 4. So factorial of n, the first time n is 4, the second time n is 3. So you have a more local binding for n, where n is actually equal to 3. Next one down is n is equal to 2, n is equal to 1, and then you finally finish and unravel. So if this whole thing, if a list of 2 lambda calculus expressions is our third production, and the intended use is that the first element of that list is a function, and the second element of that list is the input for that function. What is coming in for A right here? What's my input for A? It's a function. Yeah, just because this is a weird value for a variable doesn't mean it can't be the value for a variable. In Scheme, and in our language that we're developing right here, functions are first-class objects. You can pass a function in as a parameter, no problem. What does this app expression say to do? It says I have a function that takes one parameter and it boils down to whatever that parameter is. The second thing says this is what I'm passing in as that parameter. So what's the output of this guy? It's a function. So this right here is the value of A right there, which is the value that was passed in for this variable A. A here was bound to a value, and that value is a lambda. So that's why the output here is that. As opposed to if I took this exact same line and I changed this guy to a 4. Now the function takes in a variable and just outputs the variable. The variable I'm passing in is a 4, so the output of this will just be the binding for A, which is 4. That make sense? So we call that third production an app expression. So if we go back and think about this from a language perspective, this is a variable name which gets resolved to its value somehow. However, we end up doing that in our language. The second one is how do we describe a function? Simply, because we don't have a lot of functionality here to work with. So functions in our language here have exactly one parameter, but this parameter here is how bindings occur. They occur at this level, right? Because this is the value that gets bound to the identifier in this lambda expression. That's where variables are bound. If I come back out here, this value in our, so this whole thing here is an example of our third production. It's an example of this guy right here, a list containing 2 lambda calculus expressions. This guy here is also an example of our third production, a list containing 2 lambda calculus expressions. So if we want to keep things, this one's the easier to understand one. What I'm doing is I am binding the value 4 to the variable A. And then I'm using that 4 right here with a version of a lambda calculus expression that is just a identifier. That's where it gets resolved. That make sense? So ultimately, this comes down to where are things bound? And where is it? So, well, the slide talks about occurs free and occurs bound. All right. So next question is what does it mean for a variable to occur? What does occur mean?
When the
So-
variable's called.
Okay. I'm going to give you some examples here. We'll throw our 4 in there. All right. So right here, we would say that A occurs, correct? We would also say that X occurs. A does not occur here. And the reason it does, well, let me add, why doesn't A occur here? Might be tough to answer that right now because we're still teetering on this what does occur mean thing. What happens in here, this is where bindings happen, right? So you can't have logic that breaks down in there because this is where a binding actually happens. Identifiers occur here. Variables occur here. They're bound here. So A occurs does A occur bound? Is this variable here, A, do we expect that it has a value based on what we can see? It has a local definition. Somebody better have passed a value in for A because A is bound here and then it occurs here. Make sense? A is also bound here, but it doesn't actually occur. A never occurs in this lambda, right? It's bound, but I never use that variable. In Eclipse, that's a little squiggly. It says you defined a variable, never used it. So I can have bindings that never get used. Now, most languages, if I have a variable that gets used that doesn't have a binding, what does it tell me? You're trying to use a variable you never defined? Go ahead.
So could we say occurs like a synonym for return?
It's a little bit weird in scheme. Maybe we could say boils down to, but even then, I don't know if we quite have enough structure in our language to even say that at this point. So occurs is where it is seen in code, is being used in code. Any place where it's not being bound. Maybe that's the best way. So a place where a variable occurs anywhere that it's not being bound. Where we see it in code where it's not being bound. Probably fair. So in this case, A occurs and X occurs. Those are the variables here that occur. Does A occur bound? Yes, it's bound by this guy right here. Does X occur bound? No. The only binding we see in here is A. So can you give me an example of a lambda calculus expression that follows this grammar where X occurs, let's see, where A occurs bound and X occurs bound. So write a lambda calculus expression where A and X occur bound. So take a second, well, take 2 minutes, and try to write a lambda calculus expression, anything that fits the rules of that grammar, regardless of whether you think it makes sense for a language. It just meets the laws of the grammar We want one where A and X occur bound. And after we do a couple of these, hopefully we get past the, right now it's supposed to feel weird. I promise you it's easy, but right now it's strange enough that we have to see a couple and see what we mean. So for this one, we can say we have our app expression, a list containing two lambda calculus expressions. The first one can be a lambda that takes in an A and boils down to A. And the second one can be a lambda that takes in an X and boils down to X. Is that a lambda calculus expression where A occurs bound and X occurs bound? Sure. Now write one where A and X occur free or not bound. All right, so this one's pretty easy. Flip those two. X occurs, but it occurs free because it's not bound there, right? A occurs, but it actually occurs free. Now, A is bound there. Does that binding bind this A? This is a scope. This is a separate scope. We're going to write the Java version of this that we're more comfortable with, right? We might come in here and we might say, let's create a couple of. So we'll say static void func1 takes in an int A, and we'll just put an X there, even though it's going to be an error. Where we'll do a system.out.println X, and then we'll have a separate one. So another function, this is func2. And this guy will take in an X and print out an A. So you look at these guys here, X occurs, right? But it is not bound. I don't have a, and really we can't worry about this in our mini language right now, but basically we have this function that lives and dies, right? And we have no variable there bound to X. Yet I'm trying to use a variable called X here. So it occurs, I'm using it, but it's not bound, hence the red squiggly. Make sense? Similarly here, A occurs, but it's not bound. All right, are we clear on what occurs means? Okay. Now, write a lambda calculus expression where A occurs free and bound. One lambda calculus expression where A occurs both free and bound. just when you started getting a little confidence. I learned that from Mr. Gonzalez. He kicks you when you're down. Okay. So A occurs bound, A occurs free. All right, get the hang of it. Got the when it occurs and where it's bound. Okay. So now we want to create a function called occurs free that takes a lambda calculus expression and a symbol and returns true if the symbol occurs free and false otherwise. So we're writing a function called occurs free that takes in a lambda calculus expression that meets our grammar that has reproductions in it, right? And this should return true if, and it also should take in a symbol, the symbol we're looking for. You know, does A occur free in this lambda calculus expression? And it will return true if A does occur free and false otherwise. So if I passed it the lambda calculus expression, that guy, and I passed it the symbol A, so occurs free here would boil down to false. A does occur, but it occurs bound. Similarly, lambda XA, A occurs, but it occurs free. So this is true. Similarly, A doesn't even occur. Therefore, it doesn't occur free. All right, take a couple minutes, take a stab at writing occurs free. It is in the book, so try not to cheat off the one in the book. Think through it based on our grammar and our productions. All right, so let's take a look. Put little comments before these guys so we can compare against it. So we want to define occurs free to be a lambda that takes in a lambda calculus expression and a symbol, and it should return true if this symbol occurs free in this lambda calculus expression. Now, one thing we need to do is we need to determine whether a variable occurs, right? So we need to have kind of two separate steps here. So what I'm going to do is I'm going to pause this guy for a second. We're going to define occurs. And this will be a lambda. We'll call this guy a predicate because it takes in a single, well, actually, it wouldn't technically be a predicate because it does take in two parameters, but same diff. It returns a single value, true or false. Lambda calculus expression and a symbol. And this guy should return true if this symbol occurs. in this lambda calculus expression. All right. So our pattern here, our cond, should kind of go through our grammar, right? So we should have a cond. Now, going back to our grammar here, if this guy is where things are bound, where do things occur? Okay, well, what's a lambda calculus expression? One of these three things. So which one of these productions represents the place where a variable occurs? Forget about binding for a second. We're just talking about identifying where it occurs. So you mentioned the place where it occurs is right here, right? What kinds of things do we expect to be right here? As far as our symbols go right now, this is the production where it occurs, the identifier. Any place where we would have resolved the variable. That's an occurrence, right? Not a binding, but an occurrence. So the question we're asking right here is, does it occur? So we'll have a cond symbol, lambda calculus expression. If I'm looking at a symbol, then what am I going to do? I'm going to return whether that symbol is equivalent to the symbol I'm looking for. This has nothing to do with whether or not it's bound. We just know whether or not it occurs. So if I'm looking at a symbol, that means I'm looking at the production where things occur. And if that symbol happens to match the thing that I'm trying to determine if it occurs, then these guys, this should return true. So if this symbol and the symbol I'm looking for are equal to each other, that means that the symbol I'm looking for at the very least occurs in this lambda calculus expression. Okay, next production. How do I check if it's not a symbol, what might it be? One of these two? Both of these guys are what kind of animals? Cat, dogs, or lists? You got Brock, you got one right. All right, so how might we identify the second production? Well, both the second and third are lists. So if I know all the rest of them are lists, what things can we always do to lists? What are some of our primitive things that we can do to lists? We can get the cars and the cooters and things like that. Now, for these two productions, do both of them, are these both lists that have stuff in them? So definitely not the empty list. So what are the things that we can do to every list that contains something? Cars and cooters, they're both on the table. So for that second production, how can we uniquely identify that as being that guy, that lambda thingy? What would the car of that list be? Yeah, let's go right here. What's the car of this list? Lambda. So I can say if EQ car lambda calculus expression is lambda. So the car of it is a lambda, that means I'm looking at that kind of thing, right? Now I want to know if S occurs. So if I'm looking at a lambda here, if S occurs, where would it occur? Right here, right? Third element. So it can't occur here. That's just an identifier. That's where bindings happen, but right now we're just writing occurs. So if I'm looking at a lambda, I want to return whatever occurs gives me for this part. How do I get to that part? How do I extract this piece from that list? This is a 3 list, right? Coder of the cooter will give me the list containing that. You're close. If I take the cooter, that's going to give me the list with this identifier thing as the first thing. Car of the cooter. Yep. So if I have this list, the cooter of this list is the list containing this list identifier and this lambda calculus expression. If I take the cooter of that guy, I have the list containing this lambda calculus expression. If I take the car of that, I get the lambda calculus expression. So I want to take the car of the cooter of my lambda calculus expression, or I can do the CADDR. And what do I want to do with that? I want to call occurs on that, passing it my same symbol. So I can also say CADDR, lambda calculus expression. So you can decide which of those you like more. One has more parentheses, one uses the shorthandy thing that probably up to this level should feel comfortable. But once you get too far beyond that, then things start getting a little, especially when you get the A's and the D's mixed together. The cadadders. All right, so if I'm looking at a lambda, then I want to find out whether the symbol I'm looking for occurs in the lambda calculus expression portion of that lambda. That is in this part right here. Okay. Else, I must be looking at one of these. So if I'm looking at one of these, when would I return true? If S occurs where? Here or here? Either one. So that's an or, right? How do I get this guy? The car. How do I get this guy? Car of the cooter, right? Car of the cooter. So else or occurs car lambda calculus expression and S. And I'll go ahead and kick this down the line. Or occurs cadder lambda calculus expression and S. First production, if it's a variable and it matches my symbol, return true. Otherwise, return false. There's no deconstructing an identifier. We're out of lambda calculus expressions. Otherwise, if it's a lambda, I'm going to return true if S occurs in the lambda calculus expression portion of that. Else, it must be my app expression, the third production, where I'm going to return true if it occurs either in the first lambda calculus expression or the second lambda calculus expression. Make sense? So we've gone right down our productions here. This is where things occur. That's where I've done my actual comparison to the symbol I'm looking for. If I'm looking at one of these guys, this is where it might occur. So check it. If I'm looking at one of these guys, it could occur here or it could occur here. So check both of them. All right, makes sense? See how we're breaking these down into how the grammars and the productions tend to be the almost a pseudocode version of our things. So now we know whether something occurs. But now we want to find out whether it occurs free. What does it mean for something to occur free? So it has to A, occur, and B, not be bound. So we could write another function here for like is bound. Would be a helpful, we're deviating a little bit from where the book goes with this, but that's okay. I think this is maybe cleaner. So define bound to take a lambda calculus expression and a symbol. And this guy returns true if that symbol is bound inside of that lambda calculus expression. Remind me, where does binding take place? This guy right here, right? That's where binding happens. All right. So if I'm looking at this production, can binding occur here? No. So if I have a bound and I'm looking at one of these guys, it's just false. This isn't where bindings happen. So false. So cond symbol lambda calculus expression. If that's what I'm looking at, one of those guys, it's false. Bindings don't occur there. I don't care if that guy is this guy. That's not where he would have been bound. Just false. Okay? Else, if I'm looking at the car of my lambda calculus expression being a lambda, so that's how I can identify my second production. All right. If I'm looking at that, then I care about the binding, right? Okay. How do I look at the binding there? So really I'm asking, how do I extract this piece? Carve the cooter gets me the list containing that identifier. Carve the cooter, the catter. There might be a R rolling in there somewhere. It's French. So I need the car of the cooter. The cooter gives me the list whose first element is the list containing this identifier. The car of that gives me the list containing the identifier. The car of that gets me the identifier. So the car of the cooter. So equal CAADR, lambda calculus expression, and S. So I just return whether or not that guy is true. What if they don't match? Does that mean a binding doesn't occur? If I'm looking for the variable A and I didn't find a match right here, am I done? Or could this guy have another lambda production inside of it? So it's an OR. So I'll return true if either this guy is true. If I have a binding right here, I don't need to look anywhere else. He's bound. But if I don't have a binding right there, what do? I'll call bound on, now I need this last piece. That's the car of the cooter. CADDR, lambda calculus expression, and that symbol. So if I'm looking at a lambda, I'm going to return whatever OR returns for the binding I see right now. Does it match the thing I'm looking for? Or is the thing I'm looking for bound in the body of that lambda? All right, what if I'm looking at one of these? Same thing. Else, or bound car lambda calculus expression and bound CADR lambda calculus expression. So that's bound. All right, so for occurs free, for something to occur free, it must occur and not be bound. So occurs free in this guy means and occurs lambda calculus expression S and not bound lambda calculus expression S. Oh, thank you. Which part?
Like the second part of the comment.
This guy? Is this what you're talking about? Will this guy automatically return true or false?
Would that automatically return true? Like the first line we say.
Yep. Well, an or is a Boolean operator. So the result of an or is always true or false. One way or another. He has to kind of wait for the result of this part. You know, we get a Boolean out of this, right? So if that one's true, an or is always true. We're done. Otherwise, we have to wait for this to unravel, but an or is a Boolean operator. We'll get a true or false out of that.
So for the first part, if that predicate returns true, we want it to return false. Okay, the first line.
This guy right here. Right. If this guy is a symbol, it doesn't matter whether or not it's the symbol I was looking for. This isn't where things are bound. So if it's a symbol, that's great. It's just nothing I can look into anymore. Bindings don't occur there. So as far as I'm concerned right then, it's false. Now, he might be the false of an or. So it doesn't mean that the whole thing's going to be false, but he's a part of it is false. But as long with an or, as long as at least one part is true, the whole thing can be true. All I'm doing is when I finally, if I'm deconstructing a lambda calculus expression, and we can create complex lambda calculus expressions even though they're not impressive looking in and of themselves. I can have, you know, lists inside of lists inside of lists of lambda calculus expressions. Anytime I run into this production right here, bindings cannot occur there. So it's false. Looking at it through just that lens, that one little window. That false could be part of nested ors that call a whole bunch of other things. So it could ultimately turn into a Boolean expression that boils down to true. But at least at that corner, it's a false because bindings don't happen there. So for occurs free, we have, it has to happen, both things have to happen. It has to occur in there and it has to not be bound. And what about occurs bound? It has to occur and has to be bound. Make sense? All right, question, we're at 225 or 235? All right, questions, comments, concerns, bribes. So I'll put this code up so you have some of that as examples. You have a different version of it in the book as well. And then I'll put the homework assignment up. So for Tuesday, it's 1.29 and 1.30. Really, once you do 1.29, 1.30 is the same. You're just putting in a different version of the predicate, or a different version of your comparisons. Go ahead. You could be, but I mean, that wouldn't hurt you, but I'm not going to like test you over something I don't cover in class. So the book's a little bit of a weird read. So, I mean, if you want to put yourself to sleep, that's okay. And there's probably situations where you're doing something, you want to say, oh, I wonder how you might do this. You might find an example in the book, but I don't know if like reading it is going to give you too much help in the big scheme of things. I'm certainly not going to ask you a question that I didn't cover in class.
I was just wondering, at the beginning of class, you were like, did you cover this in the book?
Really, I'm asking, yeah, I get what you're saying. Yeah, really, did the book introduce let's? Because sometimes the book will give examples and they'll start using let's. But yeah, I get what you're saying. Yeah. Okay, I'll see everybody on Tuesday. Any questions from the online folk? Or did they already leave?
I'm still here.
There was just a squeak. It was like a squeaky toy.
Yeah, my dog.
Oh,
I was listening
yeah, I thought it was just you.
in the bathtub with rubber ducky.
All right, later.